One.
All right. So yeah, I'm Francesco from the University of Bari, and I'm going to talk about this paper recently published on the archive with Daniele Montanino, Alessandro Mirizzi, and Francesco Capozzi about the production of Axion-like particles from primordial black holes. Now, primordial black holes are supposed to be formed in the early universe by the collapse of density fluctuations. And they've actually been a very active topic recently in modern cosmology, as they've been invoked to explain various phenomena, including the formation of supermassive black holes, or explaining some gravitational wave data, and also explaining the origin of part of dark matter. Now, the formation of primordial black holes actually relates their mass to the formation time. So we see that there is a proportionality between these two quantities. And also, since primordial black holes behave as a matter component of the energy content of the universe, we see that the ratio of the density of black holes to the density of radiation grows as the scale factor of the universe, so that it is actually possible that a phase of early matter domination is attained, and this is shown in these plots where we see that the density of black holes saturates at 1. Now, in particular, we can constrain the formation of these black holes to have occurred between inflation and Big Bang nucleosynthesis. Because if they were to form after Big Bang nucleosynthesis, of course, they would alter the process. And so we can constrain their mass in this interval here. Now, after they formed, primordial black holes tend to evaporate due to Hawking radiation. And so in doing so, they reheat the universe and they lead to the standard radiation-dominated phase. Now, for an uncharged and non-rotating black hole, the Hawking emission rate is given by this formula here, where we have the black hole temperature given by this formula, and where we have these gray body factors, gamma S, that essentially distort the spectrum relative to a purely black body spectrum. So a property of Hawking radiation is that it is democratic, meaning that all particles are emitted as long as their rest mass is below the black hole temperature. So in this particular case, we see that all very light black holes are also very hot, and so all standard model particles are emitted, plus in our hypothesis, we have one light, no, not necessarily light, Axion-like particle. So we see that Hawking evaporation of primordial black holes can be a very interesting non-thermal production mechanism for ALPs. So what we do essentially is to use standard cosmology to compute the spectra of these Hawking radiated particles, and we see that the energies mainly lie in the keV range, so they correspond to soft X-ray frequencies. The spectra are independent of the initial black hole fraction, because we assume that evaporation happens mostly during the phase of domination. And also we see that if we assume a monochromatic distribution for the mass, so we assume that all primordial black holes have the same mass, the spectra have longer tails at high energies for higher masses. Now, the signatures of this model mainly come from the ALP-photon coupling. And so here we can distinguish two cases, which are the case of ultralight Axion-like particles, so with masses less than about 1 nanoelectron volt. And in this case, we see that the relevant process is that of convergence between Axion-like particles and photons, which can happen only provided there are some cosmological magnetic fields around. On the other hand, we have the case of heavy ALPs, so with masses roughly greater than 10 electron volts, where we see that the relevant phenomenon is that of ALP decay into photon pairs, and this can happen spontaneously even in the absence of magnetic fields. Now, these processes both produce high energy photons, and these high energy photons can contribute to at least two phenomena, which are the formation of a cosmic X-ray background, or CXB, which is directly measured by experiments that are, some of which are listed here. And also we have a contribution to the history of reionization of the intergalactic medium, which is measured by the Thomson optical depth tau. Here we just summarize a bit the most recent bounds on the ALP-photon coupling. So we see that in most of the mass range, these bounds are between 10 to the minus 12 and 10 to the minus 10 GeV to the minus 1. Now, just to summarize a bit the ALP-photon mixing, we of course start from the Lagrangian with the kinetic term for the ALP, the kinetic term from the electromagnetic fields, and the interaction term. And in a constant magnetic field, we see that the Euler-Lagrange equations of the system take this form. So we have terms corresponding to the ALP-photon polarization, terms corresponding to the ALP-photon mixing, and a term corresponding to the ALP mass. If we choose the photon polarization states as parallel and orthogonal to the external magnetic field, we see that actually this is a 2x2 mixing problem, since only the parallel photon mode mixes with the ALP field. But this is a 2x2 problem in a constant magnetic field. If we switch to primordial magnetic fields, we have to make some kind of assumption about the structure of these fields. So we assume that they are organized in domains with a typical domain size of about 1 megaparsec at present. So in doing so, we need to account, of course, for the expansion of the universe. We need to treat this as a full three-dimensional problem, because the direction of the magnetic field changes between domains. And also we need to account for the photon absorption by the intergalactic medium, which happens at a rate given by this formula here. So essentially, we used a result from this paper here, in which both Alessandro and Daniele were involved, to compute a recursive probability formula for the ALP-photon conversions, so that the conversion probability in each domain can be expressed as a function of the conversion probability in the previous domain. And using this probability formula, what we can do is to evaluate X-ray fluxes. So in general, photon fluxes from conversions, which are obtained by multiplying the ALP fluxes by the corresponding conversion probability. So we obtain this result, and essentially to constrain ALP-photon mixing, we can impose that the fluxes are less than this CXB fit here that we have taken from this work. Now, a bit of this is a topic that I would like to treat pretty quickly. But we can also account for the soft X-ray excess from galaxy clusters, which is a known phenomenon consisting in the fact that the spectra of many galaxy clusters have this excess radiation in the soft X-ray band, which isn't really explained by any model. And it was suggested that this could be due to the convergence of a cosmic axion background inside the cluster magnetic field, which is of the order of some micro Gauss. And we have simply applied the procedure outlined in this paper to see that a similar result can also be reproduced if these ALPs are produced by primordial black holes. Now, the other important signature of ALP-photon convergence is an impact on the ionization history of the universe. So this history, we recall, starts at recombination when neutral atoms form, but then as the first, it is followed by the formation of neutral atoms is followed by the so-called cosmic dark ages, where no luminous sources are visible. But then, as the first stars and galaxies start to appear, they trigger a process of reionization, which leads to the present situation in which the intergalactic medium is fully ionized. So we see that the situation is represented here by the solid black line, where we have that the ionization fraction drops at recombination and then suddenly rises at reionization. And we see that these three colored lines here account for the ALP-photon conversions in the light case, whereas this green line accounts for the ALP decay in the massive case. So in both cases, we see that there is a contribution to reionization from these processes. What we do essentially is to calculate the contribution from of free electrons produced in each domain by this formula here, and then plug it into the Thomson optical depth, which we can compare to the observed value by Planck. And so by doing so, we obtain these bounds here. These are the bounds from the cosmic X-ray background, and these are the bounds from the reionization. And we plot these bounds in the parameter space, which spans the primordial black hole mass and the ALP-photon mixing parameter, because they are essentially insensitive of the ALP mass. And we see that in both cases, we have significantly stronger bounds than the previously obtained ones. So this was the case for light ALPs converting into photons, but we also have the case of the decay of massive ALPs. So we see that the decay rate is given by this formula here, and we can say that it is roughly relevant for an ALP lifetime, which is less than the age of the universe. This, however, accounting for the fact that, including the fact that there is a Lorentz boost because ALPs do not decay at rest. But this prompts us to focus on heavy ALPs, because they need to decay at a high enough rate. So in this case, to obtain the photon spectrum, we essentially solve a Boltzmann equation, which includes absorption and production terms. So absorption from the intergalactic medium and production from the ALP decays. And what we obtained are these bounds here. Here we only show the bounds for reionization because they are significantly stronger than those from the CXB, but we compare them to those that were obtained by Kadamura Redondo in the thermal case, in the case of a thermal production of ALPs, both for reionization and for the CXB. So to conclude, we have seen that a domination of primordial black holes is a possible occurrence in the early universe, and it may lead to several observable signatures if these black holes emitted Axion-like particles. So we have seen that we are able to place very stringent constraints on the ALP-photon mixing in this scenario. And as further developments, it would be nice to include the gravitons in the picture and graviton-photon conversions, which happen pretty much the same way as ALP-photon conversions. Since gravitons have a higher spin, a viable production mechanism for these particles would be that of the evaporation of spinning primordial black holes. But for now, this is all. So thank you for your attention.